Hi, let's take a look at the high voltage differential probe. In this case, the Lecroy AP031. Now, I don't believe this is actually designed by Lecroy. They just rebadge it from someone else. I actually forget who the original manufacturer is of this thing. And these are an essential tool for safe operation of your oscilloscope, measuring not only high voltage stuff, but measuring high common mode voltages, things like mains, power supplies, and things like that, which you can't do really safely with your regular oscilloscope probe. And I've done a whole video on that, so click here if you haven't seen it, how not to blow up your oscilloscope. So it's a vital thing to understand that, but one of the ways, of course, how not to blow up your oscilloscope when measuring stuff is to use one of these high voltage differential probes. It allows you to measure your circuit. Just hook this onto basically any part of almost any circuit within reason, be it a high voltage mains power supply or whatever other high voltage systems, three-phase stuff. Doesn't matter what it is. You can hook these two probes up to any part of your circuit. By the way, I've lost my black probe hook here. It's around here somewhere. Anyway, you can hook these up to any part of your circuit and you will be completely safe. And then you just plug the other end, the output. So this is the input, and you just plug the output into your oscilloscope. So it converts the differential signal on here, hence the name, the differential probe, and converts it to a single-ended signal which goes into your oscilloscope. Now, these generally don't have a particularly high bandwidth. I think this one's about 20 or 30 megahertz or something like that. So it's, not designed for really high-speed stuff, but that's not the point. The point is that it has not only a 10-to-1 range, i.e. like a times 10, your regular times 10 probe, it divides your input voltage by 10 that you're familiar with on your oscilloscope. It's also got times 100 as well, or divide by 100. So they correspond to a range of plus minus 70 volts on the 1/10th range, and the 1/100th range has plus minus 700 volts. And it's got a common mode voltage of plus minus 700 volts. So a brief recap on what common mode voltage actually means here. Now, this differential probe, it's just a differential amplifier, just like, say, an op-amp is a differential amplifier, but an op-amp, of course, has a ridiculously high gain. This one has a relatively small gain of either times 10 or times 100 to compensate for the input attenuation here. So we can put up to 1,000 volts RMS across here, and, well, that's no problem. But what we're really concerned about is this common mode voltage, and this is where you can come a gutser, and I've done that video, how to not to blow up your oscilloscope. What that common mode voltage means is it's then reference to the output here. The ground of the output, the common of the output here, is connected to your oscilloscope, and that's then connected through to mains earth. I did that as a circuit ground. Maybe that should be a mains earth ground. But then it's the difference in voltage between your mains earth here and either of your input voltages. So I've drawn that as a voltage source there between any of those inputs. And in the case of a high voltage differential probe like this, that can be up to plus minus 700 volts between the output here. I've drawn an extra terminal there, I probably shouldn't have drawn that, and the output and either of the input terminals. And that's important when you're measuring, say, a mains power supply or something like that, and it is very high relative to the earth on your oscilloscope. Now, there's a common misconception about these high voltage differential probes. Some people think that they are isolated probes, i.e. they have like a transformer in there to isolate the input from the output like this, and nothing could be further from the truth, and we can prove that. The only thing we need is a multimeter. Let's measure between, say, the positive input and our output ground here, and I'm not touching it, so it's not my fingers in the way. Look, 4 meg, okay? And that's a very consistent 4 meg. I mean, we can swap that over, so if there was any, like, active circuitry stuff going on, you'd expect it to change. But it doesn't. Look, it's exactly the same. So we've got 4 meg between either of these inputs here and the output ground. And we can repeat the exact same thing for the negative input terminal and the output ground. You guessed it, it's that 4 meg again. It's very consistent. It is not isolated. And we can demonstrate that again using our high voltage mega here. So we can select 500 volts because we've got a 700 volts maximum here, so we don't want to do 1000 because, well, we could blow the arse out of our high voltage differential probe. They're not completely infallible. They have ratings for a reason. So we're connecting between the output ground, which goes to our oscilloscope, and the input. So we'll be able to measure that same resistance we got before, but instead of this multimeter only working at, you know, a couple of volts, this thing will actually test it at 500 volts. So here we go. Let's test that. And bingo, we get the same 4 meg. It is genuinely a resistance. This thing is not isolated. So how does this thing work if it's not isolated? Well, those resistance readings might have given you a bit of a clue, but there's only one way to find out. You know what we say here on the EEVblog, don't turn it on, take it apart. And needless to say, this puppy's going to have a fair bit of shielding inside there, so we might have to crack that open. In fact, we might have to desolder some cans to get to the front end. Practically all of it is shielded. We've got 2 separate sections here. So our output's from here, so I'm guessing that this is the input and this is the output can, and maybe this is just some power supply stuff up here, just keeping that separate. But look, we've got at least a couple of trimmers on there. There's another couple of holes, so maybe they've got some trimmer caps down the bottom. These are obviously 10-turn pots here for frequency compensation and other sorts of trimming. And I got this can off here. It was just very lightly soldered onto the sides here, but it looks like this one has a couple of solder points down here. These tabs are actually from the can. Thankfully, they're not all soldered. They just tacked it down. So hopefully I can, and probably another couple of points over here. But anyway, we can start to see the structure of this thing. Note our high voltage isolation slots here and here, here, and here like this. So here's our input. There's obviously 2 separate sides to this. This would be like a symmetrical because it's a differential type probe, but I wonder what we're going to find under here. You might be able to start guessing. And we're in like Flynn. We've got ourselves a high voltage isolation shield here just so that nothing arcs or shorts over to the metal can, of course, and that's important because we've got a lot of through-hole components here, vertical. Check it out. It's all a bit how you doing. But look, numbers rubbed off the chips. Mongrels, they don't want us to know what these are. They're probably, you know, they're just op amps, right? They're just sort of, you know, not jelly bean op amps, but they're not going to be anything hugely special. Now take a look at what we've got here, straddled across the isolation slot going right down here. These are all of our high voltage input components. So you can see we've got ourselves some ceramic caps here. These will be for frequency compensation, as we'll see, and they've actually heat shrunk those, maybe to provide it's not maybe some insulation, but they're just around them like that, so maybe some explosion protection or something like that, like they do in MOVs for you know, input MOVs on multimeters and stuff like that. That might be my guess, but like, you know, there's some resistors in here that are bent over, so they're obviously maybe trying to isolate the leads on there, but then that's all exposed. And well, anyway, we've got some resistors here. It looks messy, but let me try and buzz it out. Now you'll actually notice that it's virtually completely symmetrical, and that's what you'd expect from a differential front end like this. So we got, oh no, thought we had a component missing in there. Nope, but let me buzz all this out and I'll get you a Dave CAD drawing. And this is designed and or laid out by Mr. Wu. Good on you, Mr. Wu. And it's Sapphire. Yes, I believe that's the original equipment manufacturer. They're the original designers of this thing, and it's rebadged under many different names. So if I take off that heat shrink, you can start to see some of the structure here. Here's our input wire, our negative. Our positive side of this circuit's going to be absolutely identical, of course. And that's in series with another resistor, just end on end. I love how they've even got the silkscreen symbol down in there for 2 end-to-end resistors like that. That's kind of neat. So there's 2 1 mega resistors in series, and then that goes down to another 1 mega resistor, which then goes over the high voltage isolation slot there, and bingo, into another 100 mega resistor down into there. 1 meg, 2 meg, 3 meg, 4 meg. Does that ring a bell? And they've just got some 6.8 Huff caps there. They all 6.8, yep, but they're 1 kilovolt jobs, so they're high voltage ceramic caps, of course, and these don't connect anywhere on the underside, so if we go on the underside there, you can see that the capacitors don't actually connect, so it's not like you've got one capacitor across each resistor there, so it looks like we've got three series caps across the entire string of those 4 1 meg resistors. And of course they could have used one big high voltage capacitor across there, but hey, it's not easy to get greater than a 1 kilovolt capacitor, so they just use 3 1 kilovolt ones in series, which gives you your voltage. Likewise with the resistor, they could have used just one big ass 4 meg resistor on the input there, but hey, you wouldn't have got the high voltage isolation. When you string components in series like this, the voltage ratings of each resistor and each capacitor add up. So that is effectively 6.8 divided by 3. It gives you your capacitance, and then the voltage rating is 3 kilovolts total. And I do like how they added this little metal shield here over this front end where the cables come in. That just seals up the gap in the can there for the cable entry. Someone was thinking. Mr. Wu was thinking. Good on you, Mr. Wu. And you don't want the crap leaking out of your switching converter. That's why there's 2 inductors there and there, L1 and L2. After putting a bit of spin on that chip, it turns out someone at the Taiwanese factory is not very good at scrubbing off those numbers. So in true EEVblog style, we'll just speculate on what's going on here. Let's give it a go anyway. I don't plan on really doing a full reverse engineering of this thing because it's a bit of a pain in the butt and I'm feeling a bit lazy today. Anyway, so I just wanted to show you that it wasn't an isolated probe, basically, and it was using input dropper resistors, high value dropper resistors to limit the current and provide that attenuation ratio on the front end. So anyway, we've got our positive and negative input here. We've got our 4 meg of resistance here, 4 meg worth of resistance here. We've got some compensation caps around here and around here. Then the 2 resistors in there are going to be the lower end of the divider. So we've got a 4 meg input divider, and then it's going to go over to these 2 resistors here. Why they've got 3 caps, they actually look to be, they're all in parallel. So I don't know why they've got so many in parallel. Anyway, we'll have a look at those values maybe to compensate for each frequency range, which is a common technique for like bypassing, for example, because they all have a different impedance and characteristic based on their value and their package size and everything else. But they're all identical ceramic capacitors, so that's a bit unusual having 3 in parallel. Anyway, 4 meg input resistor, whatever value that is down in there, haven't looked at it, so that'll give a fixed division ratio on both the positive and negative input. This 10-turn trimmer here, that's probably just used for an offset adjustment thing, and then we've got some trimmer caps in there just to trim these 2 values in there. And you probably saw the holes in the metal case, wherever that is. I think it's over on the other bench. But yeah, you can get to these after the fact, after you've soldered in the metal can, to trim those. And then it looks like you've got the output of this going over to here, another output going over here. That's going into this metal can package here. Haven't actually looked at that one yet, but based on the number of pins there and a common technique used in scope front ends, which I'm sure we've seen before when I've done scope teardowns and things like that, that's probably going to be a matched JFET pair. Very common to use a JFET differential, roll your own JFET input amp. So I reckon that's what's going on there. That's probably a quad op amp, and this I see up here, what would that be? Okay, here's our output. It's probably coming, yeah, it looks like it's coming from there. So, yeah, it's coming, yeah, there's the output coming over there. So, yep, that's got to be our output driver. So that's converting the differential output. Well, I'm not sure. Anyway, not sure of the arrangement of the op amp there. That's, I don't know. Anyway, I reckon it's differential all the way probably through to there, and then differential to single-ended cable driver. So that's just like a high spec, high slew rate, low noise op amp or something like that to drive the output. And Bob's your uncle. We've got another couple of trimmers in here. I don't know what they'd be doing. Maybe some offset stuff, things like that. There's another couple of trannies down in there. Two of those back to back, but not sure. It's maybe with some sort of, I don't know, is there some sort of current mirror or something going on there? I'm not entirely sure. Anyway, that's going to be the basic arrangement. And I tell you what, I think they've tried to actually scrub the number off that can. That's kind of what it looks like. Marks don't really show up. Oh, is that a 3968? Is it? So let's go to DaveCAD Reverse Engineering Edition. Please excuse the crudity of this model. I didn't have time to build it to scale or to paint it. This is a very, very rough schematic of what's going on here. In fact, I'm not actually entirely sure what's going on here. This chip, which I thought at first, oh yeah, that's going to be an op-amp, a quad op-amp, but I don't actually think it is. Anyway, let's have a look at this thing. As we've seen, we've got our 4 1 meg resistors in series and our 4 6P8 caps in series for some frequency compensation on that. And they're all their 1000 volt caps. And they're going into the 25K here and the trimmer, which is just used for an offset balance adjustment there. So, you know, we've got a pretty good division ratio here. This is why it can survive and measure all the high voltages. It's basically differential input, and then I believe it's going into a dual matched JFET here, because this is very typical front ends, although I couldn't really find any info on that part number that I saw down here. It said it was like an N-channel JFET, but it didn't say it was dual or anything else. So from some obscure company that's probably not even around anymore. Anyway, I believe that is a dual JFET input. That makes sense. We've got some diode clamp in here for input protection. By the way, these 3 caps here, 120 puff, 82 puff, and 82 puff, and then probably a much smaller trimmer cap value here, just to trim the frequency compensation on this thing after it's all assembled and the metal cans, everything else is on. You get in there and hold your tongue at the right angle and tweak these, tweak your balance adjustments, and there's a couple of other pots in here which I haven't reverse engineered and shown. So it's kind of unusual that they've got the 3 in parallel. Not entirely sure why they're actually doing that. They're all the same type of ceramic, so maybe they're just trying to get a tighter tolerance or something by putting the 3 in parallel like that. That's all I can think of, so that the trimmer has a better, more accurate, more controllable adjustment range perhaps. Anyway, going into 2 JFETs, and then after that, I'm not sure what that puppy there's doing, but by just looking at the pinout and everything else, it doesn't seem to be an op-amp. So what I think it is, and because it just didn't make sense in this sort of arrangement here to have an op-amp directly on the output here, it's not that one, forget that for a second. A differential JFET front end like this usually needs some extra transistors here, and usually forming a current source down here. So that's the usual arrangement. So I think, my guess is that that puppy's actually one of those transistor array chips, and I couldn't make heads or tails of the number. The partial number that I got off that certainly didn't make sense in terms of a quad op-amp part number. So I believe that's some form of transistor array. They were quite common back in the day. You can still get them in various forms. TI and other companies make them and stuff like that, and lots of obscure providers back in the day. Matched transistor things. The reason that they're good is because they're matched on the same die. If you try and do a discrete front end like this with all separate, 2 separate JFETs and then separate bipolar, usually bipolar transistors, it won't be JFETs, so these will be BJTs in here. So I'm missing a whole section of circuitry there. I mean, this is not just 2 resistors and a current, there's going to be, like usually these have like 5 or 6 transistors, usually in a current in a differential configuration with the emitters tied together and stuff like that. Anyway, I reckon that's what that puppy is doing there. So that makes sense. And then the output, the differential output, is then going over to this puppy, which has had the number rubbed off, so I can't even get a partial on that one. So that'd be converting the differential into the single-ended driver to drive your coax over here. And that's about all she wrote. There's a couple of other transistors in there. I haven't bothered to reverse engineer all that. There's a couple of other trimmer adjustments in here, which are probably, this one might be output gain, for example, and this one here might be current source adjustment. So I reckon that's what's going on there. So if anyone actually has a complete schematic of this thing, I'd really like to see it. Anyway, this wasn't really 100% reverse engineering video. It was just to show you what's inside one of these differential probes, and then they're not actually isolated. The reason that they're safe is because they use these resistors in series like this, and you're protected. So if you're holding on to the output, the grounded output like this, and you've got hundreds of volts, 500 volts floating around in here relative to the ground that you're holding on to, you're pretty darn safe because you've got 4 meg in either lead like this, and you've got multiple capacitors in series as well. You know, like if you just had the one cap in there, you could get a single failure, then it might render it a bit unsafe. It could go through the 25k to ground, and your output, you know, this is your ground reference output here, so that could, you know, if you're holding on to that, doing whatever, then, you know, it could be a problem. But these are very safe probes just by nature of the 4 1 meg resistors in series, and the high voltage isolation slots and the rated caps and everything else. So Bob's your uncle. That's how it works. It's just a basic JFET differential amplifier with a big attenuator on the front end. And just for kicks, there's inside the DC to DC converter, and they've rubbed the number off yet again. Why protect a crummy discrete DC to DC converter? Give me a break. And we'll just have a quick squiz at what rails we've got here. Of course, nothing's marked on here. There's no voltage rails, no ground points marked. But of course, for ground, you almost always take the ground plane on, well, the plane on there, the main plane. It's almost certainly going to be ground. And then, as I think I mentioned before, we've got the 2 inductors there and there. I think this is only going to be giving out, there we go, 9.5 volts. And the other one should be negative. Similar, yep. Negative 9.5. So there you have it. That's inside the Lecroy AP031 / Sapphire 9001 high voltage differential probes. So I hope you found that interesting, just how these things work. With the front end, I mean, the exact reverse engineering details aren't a huge big deal, but the fact that it uses those 2 big resistive dividers with a differential FET front end, that's what we wanted to know. Rather interesting little beast. This one is ancient. I don't know the date on this one. They've rubbed off all the bloody codes on there. Anyway, this design must date back a long time. I got this one back when I was still working at Sercel, I think. So 5.5 years EEVblog full-time, 4 years at Altium. You know, it's probably a good 10 years ago I got this, and it was an old model back then. It might be a more modern variant these days, because it is pretty how you doing. It's all through-hole design. I'd be surprised if they haven't done a new modernized version of it or something like that, but it's probably still identical. But you probably wouldn't still manufacture that one today. I would modernize it with some surface mount stuff at least, just to, you know, just to make it neater and tidier and get your production cost down. But the design would still be as valid as it was back then. And, well, you know, some like the FET front end might have gone obsolete or something like that. The transistor array might have gone obsolete. You might, you know, modernize those or something like that. But the basic technique and everything else would remain very much similar. And there's other ones on the market as well. You can get them for like $300 on eBay these days. Not this particular model, but there's another one. Actually, I think I can get my hands on one of those. It'll be interesting to do a teardown of the cheap $300 eBay one and see. Anyway, hope you enjoyed it. Catch you next time.
Hi, I just read a post on the EEVblog forum where somebody was asking about the oscilloscope probes and how they can be potentially dangerous if you hook this ground lead up to the wrong point in your circuit. You can blow up your circuit, you can blow up your scope, bang! And it really is a big trap for young players, and I've mentioned it before, but they wanted to know exactly under what circumstances that could happen.